Now we're actually going to use power series to do some integration. So how do you integrate tangent inverse? Yeah, it seems pretty tricky. So what we could do is use a power series to replace tangent inverse. And a power series is a function of x. It's got x to the 1, x to the 3, x to the 5, etc. In fact, in the previous podcast, I found that tangent inverse of x over 2 is equal to this power series. So we'll go ahead and use that as our starting point. So we've got tangent inverse of x over 2 is equal to, it's an alternating series. It's got x to the odd powers, 1, 3, 5, 7, etc. It's divided by 2 to that odd power, and then divided also by the odd number. And this is valid for x between -2 and +2, which is fine for this. That works. Okay, so to integrate this, you would need to add 1 to the exponent, so it's going to be 2n plus 2. Then you divide by that. Or what we could do is also look at some terms and integrate those terms. So we would have first n equals 0, so this is a 1. This is x to the 1, 2 to the 1, and a 1. So we'd have x is to the 1, and then 2 to the 1 times a 1. Next, when n is equal to a 1, this is going to make it negative. This is going to be x to the 3 over 3 for this part. And then this is 2 to the 3, which is 8, but I'll just write it as 2 to the 3. So then I can already see what the pattern is, and I don't have to refer back to this formula. It's going to be, next is going to be positive. X is to the 5. It's going to be 2 to the 5th, and then times 5, etc. So if you integrate from 0 to 0.5, tangent inverse of x over 2, that's the same as integrating from 0 to 0.5. Let's see, the first one is 1/2 x. Next is minus x cubed over, I'll just leave it as 2 to the 3rd times 3 plus x to the 5, 2 to the 5 times 5, and one more, x to the 7 over 2 to the 7 times 7, etc. So by using just 4 terms, we could get a very good estimate, and then we'll go ahead and do the general integral last. So integrate this, it's going to be x squared over 4, and then minus, this will be x to the 4 over 2 to the 3rd times 3 times 4, and plus x to the 7 over 2 to the 5 times 5. Now, whoops, that's a 6. 6. And then this would be x to the 8th over 2, 7, 7, and 8. And then evaluate that from 0 to a half. So when you substitute 0, that's going to contribute nothing. We just really need to have the half. So if you have the half squared over 4 minus the half to the 4th over 8 times 12 plus, and then we'd have the half to the 6th, 2 to the 5th times 30 minus the half to the 8th, 2 to the 7 times 56. then we've got 1/2 raised to the 6th divided by 2 to the 5th times 30. And then finally minus 1/2 raised to the 8th divided by 2 to the 7th times 56. So just by using the first 4 terms, we get this as an estimate. Let's see if I can get the calculator to give us an estimate as well. So we're integrating x divided by 2, tangent inverse of x divided by 2. Need to make sure that it's in radians, and then go to the window. So we're going from 0, so I'll go -1 to +1. So judging by the graph, from 0 to 1/2, that would be a pretty small answer. Not quite sure if it's supposed to be that small. Let's see. Calculate the integral from 0 to a 0.5. Oh, very good. So at least for the first 3 decimal places, we have the correct answer. And that's just using 4 little fractions. Okay, now what I want to do to finish this up is the integral from 0 to 0.5 of, so go back to the series that we have and integrate this series in general. So integrate the sum, n goes from 0 to infinity, and then x is to the 2n plus 1 over 2 to the 2n plus 1 dx. So it's really just this part right here that we need to integrate. So add 1 to the exponent, it's going to say 2n plus 2, and then divide by that number. So we would still have series. It would still alternate. This would be x to the 2n plus 2. And then I have to divide by 2 to the 2n plus 1. There was already a 2n plus 1 in the denominator. Now there's also, because of this, 2n plus 2. And then that would have to be evaluated from 0 to 1/2. So as I said before, the 0, when it's in there, that doesn't contribute anything. We just need to have the 1/2. So we would have the series from 0 to infinity. It alternates. This is now going to be a 1/2 to the 2n plus 2, and then divided by 2 to the n 2n plus 1, and then 2n plus 1, 2n plus 2. And then because this has a 2 and this has a 2, we should actually combine those. So this 2 to the 2n plus 2 actually belongs in the denominator. So we would finally have, I need some space. Here's some space. So we would finally have that it goes from 0 to infinity, it alternates. It now has 1 to the, doesn't matter, it's 1. And then we've got 2 to the 2n plus 2, moving this to the denominator, times 2 to the 2n plus 1, times 2n plus 1 and 2n plus 2. And then finally, I suppose we should combine those. The bases are the same, so that's going to be 2 raised to the 4n plus 3.